Good morning, Year 12 single mathematicians. Just going to continue with some revision topics for the upcoming internal exams. Someone's asked me to go through mathematical proof, which is within chapter 7 in the pure textbook. And just going to start with things you definitely need to know. So you're going to be presented with a mathematical statement. It could be something which might be something very basic. It could be an identity. It could be an inequality you're asked to prove, or it just could be a worded statement. Might even be a geometry problem, all sorts of different things. And then you will be decided to either prove the statement is true or false. So when you prove it's true, that's called a method of proof, and we're asked to show a statement is false. That's a method called disproof. Now there are various methods for both. So the easiest one is to prove something is false. You find a counterexample, which is just one case which contradicts the statement, so proves the statement is false. Okay, so counterexample is to find one case where the statement is false. And the easiest type of proof, so when you've got a statement which is true, is by exhaustion. Okay, which requires you to check all of the cases one by one. So you check each case individually, one by one, until you've checked them all. Okay, now this type of proof doesn't work if you've got infinite cases, obviously, but if you've got a small number of cases, then this is perfectly fine. Problem is that one isn't a mathematician's favorite type of proof. Their favorite type is by deduction, and this is the one which comes up most often. And with this, you start with some obvious or known mathematical statements, facts. Then you apply logical steps, and then the third thing is you end up with the statement you want to prove. So this type of logic would work for an identity, for an inequality, for worded statements. So this is the main type of proof you need to know. Let's see how these look for EG number 1. So EG number 1, we're going to get the easy ones done and dusted, which is proof by exhaustion for part A. Proof by exhaustion, the statement that all even numbers between 10 and 20 inclusive can be written as the sum of two prime numbers. So proof by exhaustion requires you to work out all of the cases individually. So they're making a claim about even numbers between 10 and 20 inclusive. So part A, if I wrote down the even numbers between 10 and 20 inclusive, that's what I would get. And they are claiming in the statement that they can all be written as the sum of two prime numbers, and I just need to check to see if that is true. So 10 could be written as 3 plus 7, two prime numbers. 12 could be written as 5 plus 7, two prime numbers. 14 could be written as 7 as add 7, doesn't have to be different prime numbers. 16 is the same as 5 plus 11, two prime numbers. 18 is 3 plus 15. No, 3 plus 15 is definitely not going to work. So let's try 7 plus 11. That's better. And 20 would be 7 plus 13. So yes, all even numbers between 10 and 20 inclusive can be written as the sum of two primes. That's my conclusion, and it's really important at the end of a mathematical proof you write a conclusion, and I end my proof with a proof square saying the proof is over. Part B is a disprove by counterexample. So this statement is false, not true. They claim that the sum of two prime numbers is always even, and there must be a case where this doesn't work, and I've just got to find one of those cases. So try and think of two prime numbers. When you add them together, the answer is not even. Let's consider 2 plus 3. Those are two prime numbers. If you add those together, it is 5, which is not even, and that is your counterexample. Okay, therefore the statement is false. No proof square for this because you didn't, it was a disproof one. And that would be it. That's the two easy ones done. Let's move on to the deduction one now, which is these 3 steps. Start with some obvious known facts, apply some logical steps, and then end with the statement you need to prove. Three statements. Statement 1 is an identity. For an identity, you start with the more complicated looking side of the identity, then apply your logical mathematical steps and end up with the other side of the identity. So I would think the right hand side is the more complicated looking side. So the right hand side looks like this. And now I'm going to apply logical mathematical steps until I get the left hand side. So the only step I can think about is expanding the brackets, which would give you x squared plus bx. I'll actually write this out in full. B over 2x plus b over 2x plus b squared over 4. Expand these brackets, subtract b squared over 4, and collect like terms. Well, they disappear, and you'd be left with x squared plus b over 2x plus b over 2x is the same as bx, and that is the left hand side, which is equal to the left hand side. Therefore the statement is true. End of proof. Identities are a little bit easier than the others. Okay, part B. Prove that all square numbers are either a multiple of 4 or one more than a multiple of 4. So this is one of those worded statements now. Okay. Sometimes it's not entirely sure what you're actually being asked to prove. So I'm going to write out some of these square numbers they're making statements about. So square numbers, for example, 1, 4, 9, 16, 25, so on. Now this is not a proof by exhaustion, but let's try and see what they're actually claiming. So they're saying that they're either a multiple of 4 or one more than a multiple of 4. Let's see. Number 1. Well, that would be one more than 4 times 0. So that's one more than the multiple of 4. 4 is 4 times 1. That is exactly a multiple of 4. The number 9 is one more. 4 times 2 plus 1. The number 16 would be exactly a multiple of 4. And number 25 is 4 times 6 plus 1. One more than the multiple of 4. So it looks like we've got this pattern of one more, exactly a multiple of 4. One more, exactly a multiple of 4. One more, so on. So the odd square numbers are one more, and the even square numbers are exactly. Now this allows me to actually start the proof now, because there's two cases. So I'm going to consider the even square numbers and the odd square numbers separately. So case 1 would be odd square numbers. So if it's an odd square number, then we're going to consider an odd number, which is something like 2n plus 1 is the general odd number. But we want a square number, so we're going to square it. When you square that, we need to try and prove that this is always one more than a multiple of 4. 4n squared plus 4n plus 1. How can I show that's always one more than a multiple of 4? Factorize a 4 out. 1 more than a multiple of 4. Okay. The other case. The even square numbers. These should always be exactly a multiple of 4. This time we consider an even number, 2n. But we want square numbers, so 2n squared, which is equal to 4n squared, which is literally a multiple of 4. And we've considered both cases. Odd numbers give one more than a multiple of 4. Even square numbers give exactly a multiple of 4. Therefore, the statement is true. And that would be it. It's really important that if you've got multiple cases, you check them all. And sometimes just trying to work out what's going on gives you some indication on what the pattern is, and then you can prove it from there. Right, part C. We have an inequality. X over y plus y over x is greater than or equal to 2 for all positive values of x and y. Right, so let me write that inequality down. X over y plus y over x is greater than or equal to 2. Now, the inequality type, you kind of cheat a little bit. You actually pretend the statement is true, and you do our sort of 3 steps from before, but in reverse. So if I remind you those steps, the last step was end with the statement you need to prove. I'm going to start with a statement, then I'm going to work backwards and apply logical steps, and I want to end up with something which is obvious or a known fact. So let's try that. Remember, x and y are positive. It's a key thing in this. Right, what would I do if I had this? Well, I don't like fractions, so I would get rid of the fraction. So I would times everything by the denominators x and y. So let's times by xy times by xy. What would this simplify to? Well, that would be x squared. Second term would simplify to y squared, u times yxy. The inequality sign would not change direction because it is times in by a positive number, so that's greater than or equal to still. And 2 times xy is 2xy. That would be fun. What would be logical to do next? It's kind of like a quadratic, so I would make it maybe something to 0. So x squared, subtract 2xy plus y squared is greater than or equal to 0. Okay, so the quadratic, normally they factorize. Does this one factorize? Yes, it does. It would go to x minus y squared, which is greater than or equal to 0. And now, this alarm bell should go off. This is an obvious / known fact. Something squared is positive or greater than or equal to 0. My proof is almost ready now. All I do is rewrite this but in reverse, because I always want to start with this known fact and finish with the proof. So I will write the known fact. So consider x minus y squared, which is greater than or equal to 0. This is a known fact. What I did above was expand the brackets. Expand the brackets. Then you took the thing to the other side, so take the thing to the other side. Then divide by xy, so divide by xy. And it goes to this, x over y plus y over x greater than 2. The inequality doesn't change direction because x and y are positive. And that is the end of the proof. So the actual proof is the thing on the right. The thing on the left were my workings, and in the textbook they call these jottings. And this is the type of method you do for inequality ones. You kind of cheat and do it in reverse and then rewrite it in the correct order. And that would be it. Now the questions I'd like you to do from a mixed exercise. So it's a mixed exercise on page 155, and if you start at question 15, and these questions go up to 25, and just try a mixture of these types of questions. So try a proof by exhaustion, try this proof by counterexample, try proving an identity, try proving a statement, a worded statement, and try proving an inequality. And then that should be it. Any questions, rejoin the meeting and ask me.